another Draft Physics video production. Having a few technical issues. Hopefully they will not cause any major problems. Anyway, a couple of comments, then we'll probably go to the drawing board on the subject of polarization some more. And such. I was going to read some Piro video comments, but on Piro's video, but they're all irrelevant on politics and such, so it was kind of funny. The subject apparently of science denial doesn't carry much weight with his viewers, but anyway, it's kind of a nothing comment, frankly, just one man's opinion. First time someone explained physics to me, I don't have 1 minute more questions. I just understand and it makes sense. Thanks for this. Okay. We'll see how that goes. Yeah, see how long that lasts. I have learned to be cautious, like a scientist should be. You can't take anything too seriously, too fast. Can't jump to conclusions. Anyway, so that brings up Stephen, because he's sort of a conclusion jumper. But anyway, alright, hi Gary. You mentioned yesterday, I might as well read this, just to be fair. You mentioned yesterday that it would be helpful to know whether anyone had done the microwave version of the polarizer paradox thing. Seeing as I had the bits handy, confident it would work the same, I thought I would give it a quick try. Well, I wish you'd do the quick try on the putting the receiver in the middle, between two emitters, emitting at the same phase, and see if you pick up an interference pattern by moving the little thing in the middle. Alright, initially I had to concede you appeared to be right. I was baffled why it didn't work on microwaves, and was left with the conclusion I had better take a closer look at your reasoning and possibly abandon my own. Well, this is the trick here. I mean, like I said, it's great that you have your own theory, but you ought to just say what it is so we understand what's competing here in terms of your expectations and experiments. As I stated in my video, I didn't have really any expectations, in the sense that you have to recognize that the two forms of the radiation, even though they're made of the same phenomenon, they're photons, they're produced in a different way, in the sense that it's very hard to create light that's in phase, because we can't manufacture the high enough frequency to create light in phase. And the radar is essentially being created perfectly in phase. Every bit of all the photons are perfectly in phase with each other. So it's fundamentally very different radiation in that sense. And then you have the whole antenna problem. And then you have a whole question about anyone's theory of how, well, probably should wait till I draw it, but a theory of how photons are created. How do the individual photons know how long the antenna was they were released from? Is that information somehow encoded into the photon? These are all these open questions that sort of have to be answered if you're going to draw any conclusions based on what the experiment produces. So anyway, but the good news is like I say, every time some of this is done, something new comes out of it, and your video does provide some new stuff. So let's go to your video. Maybe I'll read a little bit more, and then we can come back to read the rest, maybe something like that. I recorded my thought process, my head scratching and picking my nose in real time, so you can spot the eureka moment when I realized my mistake. Well, as I stated in the video, that's why I wasn't sure you could do the experiment exactly the right way, just because the light is already polarized in one sense, that it has antenna polarization. Now the question is antenna polarization different than photon polarization? And I would argue that clearly it is a different phenomenon. So sort of as I drew in the initial part of the video, I pointed out the Professor Lewin kind of experiment where you take a radio antenna and you put, you don't put a sound on it, you don't put any carrier signals. All you do is take another antenna and see if you can pick up the voltage. and light a light bulb. And when you do that experiment, when you have the antennas crossed, no light bulb. You turn the antenna so they're the same, light bulb lights, indicating that the energy, but that's a kind of polarization. Again, antenna polarization, is that really what we think light is? Light polarization is antenna polarization. The emitter is somehow polarizing the light. I don't think so. But anyway, unlike the light used to test polarizing filters and their supposed paradox. Right, so light comes out as mixed polarization, and you're filtering. And but again, is this the same kind of a polarization? Is antenna polarization the same as light polarization as we use the words? And I would argue they're not the same phenomenon. And you can sort of deduce it in a lot of different ways. And so that's what we'll do. Anyway, so this is why the experiment's good to do. Try to glean the information, but you can't draw conclusions until you've thought about it a bit. So because there's catches all over the place. So this is the bit where he realizes how he needs to do the experiment. As he does demonstrate, you really don't need to put these filters, these two that show orientation, in front of the emitters. Now the catch, kind of, is which way is the antenna oriented. Now he has a little indicator on the horn on one of them, probably indicating that the antenna inside the horn is in this direction, vertical, and that he's lining up the grating in the same direction, and that's passing the signal. The other thing to understand is the wavelength of the radar, if that's what we want to call it, microwaves, is probably somewhere around 3 centimeters. It's pretty big, and the bars are a few millimeters. So the distance between them. So we don't really have a relationship that seems to exist with light, where somewhere around the length of the wavelength is relevant to the passing of the wave. So these bars are much tighter than the wavelength, and clearly if we were going to argue that the polarization height or distance was somehow related to wavelength, it sort of just indicates that these bars should be much further apart if if the conventional theory was to be applied. But anyway, let's play the video.
I'm glad to come to a conclusion that makes more sense to me anyway. It might not make. I feel mean now though, because.
Okay, I missed the important bit.
Okay. The 45-degree one in the middle.
All right, so this is.
So now, yes. So if I put this way.
Let's move it.
Remember,
there. This is where we want it.
Yes.
So he first does it without the two filters and figures out that the diagonal does get some signal, so then he decides to put the filters in front of it just to show the orientation of the two horns, the antennas. So one antenna is apparently going horizontal, and has a horizontal filter in front of it. The other antenna has a vertical filter. Guessing.
Right, yeah. So we've got one filter one way, one filter the other way, and I've put the 45-degree one in the middle.
So you could also see when he tilts the filter, the filter is still in front of it, and yet you get a sound. So that's a little bit weird. All right.
Yeah, and it lets it through.
Right, and he's claiming it's 50%. Obviously, I think it's much less than that, but it should be less than that. It should be like 30% or something like that. But anyway, so it seems okay, similar to the experiment in light, but it does get a little interesting here.
Yeah. That's why. It's lower volume because I've turned it down because it's 3:30 in the morning. Yeah.
There, this is the part that you have to pay attention to. Now, isn't that interesting? So, the fact that it's turning on and off as he moves at a distance. All right. Now, if these are like standing waves, you could sort of make an argument that, he's moving in and out of the phase. So it all has the same phase. So in a way, it's creating a standing wave. And so in a sense, you're saying, yeah, I should be able to detect the wavelength. Now, if you could do that with light, then you'd have an interferometer, without the mirrors. I guess you could put extra mirrors in it for some reason or another. But in a sense, you'd have the detector for an interferometer if all you have to do is move the polarizing film in and out to catch the phase of the light, change which light even is going to be passed and which light isn't going to get passed. So you could change colors, presumably, or something else. I don't think that'll happen with light. But anyway, so it really is interesting, though, that the distance is consistent, I would argue, almost, maybe, with the 3 centimeters, 2 or 3 centimeters of the wavelength. So let's play that part again, because I found that just, whoa. That should have been a moment where he said, whoa, what is that?
It's lower volume because I've turned it down because it's 3:30 in the morning. Yeah.
All right. Now the other the other argument would be is what's the metal actually doing? And so in thinking about that, does it retransmit the radar? It is metal. It's going to vibrate at the same frequencies, presumably, and it can readmit the signal it receives. So when you turn it at a diagonal, you're catching more of the radiation, I would argue, just because now you're turning it back to the same orientation as the other antenna, so you're getting more radiation, and it's readmitting it now in that orientation, and that's why you can receive it, is because it's closer to the antenna's orientation. Now the trick is, though, is why is it detecting, apparently, so let's play it. I mean, it's clearly on and off, I'd say. Okay. We also don't know for sure whether that audio signal is on the radar itself or whether he's just using that afterwards. So he has a meter here that detects the radiation, but we don't get to see the meter, so it's hard to make a judgment about whether he's picking up something or not picking up something. We're only going based on, again, when the audio is decipherable, which is always dangerous, I would argue. See, I don't see any.
Yeah, and it lets it through.
I don't see the meter moving at all.
Yeah, that's why. It's lower volume because I've turned it down because it's 3:30 in the morning. Yeah.
Alright, so yeah, so we don't get anything of that. The other part is reflections. Again, reflections create more energy, so if you can reflect any of the signal off of something, and you can do it over and over again, it magnifies at the speed of light. Obviously, any reflecting energy would bounce back and forth many times and amplify any signal you're going to receive. So if the signal gets through and then reflects and back and reflects and back, and those reflection points, okay, I don't really understand how phase would change them, but maybe it does, so it's something to think about. But anyway, interesting. I just, to me, I don't even have a conventional theory, that makes me understand why phase would be detectable here, at all. But But anyway, it's interesting. So we'll go through some of the points and draw them and such, and see what we can make of this. Like I said, it did provoke some thinking, and so I have another draft proposal that sort of explains diffraction in substances, where the light bends, refraction, whatever you want to call it. Like in water, the light bends and then readmits. And it seems like this might be related. But anyway, it doesn't seem like they should be related, but it seems like it's related. Anyway, the other experiments to do is to move the filter this way, and see if that changes it. Now we know we got a different signal going this way. Like there's places where it's on, places where it's off. So you could put it in diagonally in certain locations and you get no signal. Put it in another location and you get a signal. That's revealing in some way. Anyway, it's information. It's something different. Something I didn't expect. But anyway, I'll pause and be back. Theory. Yeah. Alright, should be back. Alright, I don't know. We'll just go over this real quick. The different kinds, the stated polarization. So you have an antenna that produces, and you have a receiving antenna. And there's a difference between putting your receiving antenna horizontal to the admitting antenna or vertical. I mean, those are kind of your choices. And the simple argument is when like a radio antenna, big tall one, is producing radio waves, it tends to produce them in straight lines. Let's argue it's a straight line rays of radiation. And the radiation is all in phase. That means the on and off parts are all in alignment in terms of distance. So obviously when you start going these kinds of angles, the distance, say a photon came off of here and went over this way, it would be out of phase a little bit because it's a longer distance. But the idea is that the emitting happens in all these locations, but that the signal does start all in phase. So there's one group of photons that are all in phase. But anyway, the point would be is that the antenna is obviously going to be creating this in, both dimensions, primarily. Now, some will be going up, and some obviously goes into the ground, hits the ground, doesn't do anything useful. So it does diverge as it moves across distance. But the point would be is if you put your antenna this way, you can just sort of logically understand that all of the radiation here and here isn't going to be hitting your antenna. There's just no chance of it getting there. Because most of it is the same orientation as the antenna. I mean, it's shooting stuff out in these layers based on its height. Okay, so there's going to be, it's just not this, it's spread in this direction, so all you're getting is this one slice, where if you put the antenna this way, you'll get, all the stuff going up and down, which is thicker. There's more radiation going this way, okay, than there is going in and out, if I was to try to make an illustration of it. So the reason why that's the polarization, in the sense, is that the energy itself, the bulk of it, the amount of photons you'll hit, is polarized. So it's not really that the little bits have any polarization relevant to this antenna argument. The bits aren't saying, I came from a 5-foot antenna. It's not written on the photon itself how long the antenna was, and the antenna has to be in the right orientation or something like that. It just has to do with how much radiation you're going to get hit by argument. That there's more of it to be hit by in this position than in this position, because there's more density. There's more density going this way than there is going around the surface of the antenna. So say the antenna is round and I'm looking down at the top of it, the amount of radiation coming this way, this distance of the spread, is greater than the distance is of the ones next to each other going up. So I don't know how to, there's no easy way to say that, but for those of you who understood, you understood. So that's one kind of polarization. It doesn't, it's not the same kind as what I'm saying. Receiving polarization, I mean how much of the energy you're going to receive, like when you buy a light bulb or something. Now a light bulb's got even distribution this way and this way, because it's not a tall, thin antenna. But if you change the orientation of the light, like I said, if I created a light that wasn't a tube and I wanted to receive as much of it as possible, I wouldn't turn my receiver this way, I would turn my receiver this way. Because it's a straight line force. But anyway, okay. And the circumference is what's sort of dictating. As you can sort of understand, the circumference of the wire, the antenna this way, is a lot less than the length of the antenna. That's the part. See, the antenna is just a little bit round. This circumference is one way the light is radiating, and this is the other. And obviously this longer one, okay, surface area, more of the surface area is in this long distance than is in this circumference. And really it's not even the whole circumference that's relevant, because you obviously aren't going to see the light going the opposite way to where you are, so the only circumference that matters is this circumference, which even cuts it in more of a half. So half the radiation you can't even get to because it's going the wrong way, and so all you have is this distance versus this distance. And so that's the nature of the polarization. So that, okay, I would argue, doesn't really have anything to do with what's traditionally called light polarization. That has something to do with each photon having some sort of character. And I argued it's because of an alignment problem. Now, they argue that somehow this wave, okay, and let's understand, they don't tell you anything. They draw you this picture of this wave, and it's I guess you could draw it as a helix, you could, right? I mean, you could just do this and say, one's the magnetic component and one's the electrical one, and they're both on at the same time. But they don't make any distinction here. Is this a photon? Is that all I need? And I have a photon? And doesn't that have two nodes in it? I mean, so even if you said that's a photon, this complete wavelength, well, I mean, technically it has three nodes in it, but let's just say it was two nodes of on, okay, and two nodes of off. So even that's confusing, I would argue. And there's no real explanation in physics. They say this is a standard thing, this photon, and yet you can just logically say, well, what if you have this much? There's that a 1.5 photon? I mean, where do I begin and where do I end? Now, what they know is that there's a certain amount of this that your eye has to be hit by before you can see the photon. Like, you actually have to see 5 or 6 of these things. Or if you don't, if you only see 4, you don't see it. The photon doesn't register, the electron doesn't move, the event doesn't happen, and your eye says there's no light, it's black, it's dark. But they don't tie this stuff together in any way. I haven't seen any physicist ever talk about the ray length of a photon. And I would argue that even if you believe in wave theory, you have to concede that it has a wave length that has that he sees. You can't say, I can say ray length because then you can understand it's this whole thing, but I can't say wavelength because we've already used that word to describe this. And again, this is a description of two events, one, two. It's not a description of one event. There's it's just not. Unless you convert it, unless you realize that this downside never happens and this really is just representing one on state. So one wavelength is one on state. So you just make this a double amplitude up instead of playing this game of having two kinds of waves interacting or something. I'm just saying, but there's no description. We have no, they'll say something like they have quantized the photon, and yet they haven't quantized it. They haven't explained that the fact is, okay, that you could hit an electron with 17 of these things, okay, in a row. And the electron will just say one photon. I could hit it with 8, and it would say one photon. That there isn't any pure consistency between what goes in and what goes out. All right, but anyway, so that's what we're starting with, is some idea of this wavy thing. Now, again, I'm arguing that polarization is just an alignment issue. Just means this, like their wave wouldn't work. If I try to draw their wave and say it's got this kind of stuff happening in it, like the wave is somehow following an uneven line, they'd say, no, that's another wave then. So that's not going to work. That their wave is waving, so that wouldn't make any sense, that's what polarization is to them. So they make it into some amplitude argument that, polarization for them just means that these things have, an amplitude, a height, it's different. So, and it's in one dimension. It's going, this way, or it's going this way, or it's going this way. This field change. The field is being pushed in one dimension only, in one plane of the dimension. Something like that, but we don't even know what this thing is. It's this wave thing, which doesn't have any identity besides saying, okay, it's in a plane for some reason, and it's moving through space, vibrating in that plane, somehow, some way. Which, again, I can't, my brain just says, no, it just rejects it automatically. It's not food. It's cardboard. I spit it out. It's just not an answer. So anyway, clearly, what we're trying to figure out. So I'm arguing that the photons individually have to be carrying this thing called polarization. So in the antenna argument, well, the orientation of antennas, that's not something each photon is carrying. That's what the group of photons is telling you. Okay, that's group polarization, if you want to call it that. It doesn't really have anything to do with this kind of polarization where each photon is carrying this information about what plane it's in. Okay, so the light experiment is fundamentally different. Now, so the idea would be here in this example is that we have this phase. Okay, so you could argue that if it's all in phase, then all these little things, and we'll just say the things represent the hump. I'm just not going to draw humps, but okay, so we're just going to say the on part of the wave, or however you want me to say it to be compatible with your wave crap. Okay, and the idea would be is this is traveling through to this other receiver in the radar experiment. And what we saw Steve do was he moved the filter through that field and was able to see, we could say, to detect the standing wave that would be essentially created with everything in phase. With everything in phase, you'd figure there'd be a standing wave, and he essentially was detecting that standing wave. Now that's one way of interpreting what we saw. Now, the other way to interpret it is what would happen if, again, the signal does get to the bars and it reflects and it readmits and it reflects and it readmits and then it gets through. Now its phase is going to be different. Okay, it's going to have a different phase because it traveled a different kind of distance. So as soon as you change the distance that the stuff is traveling, it'll end up being at a different phase. So the on parts of the reflected wave are going to be very different than the on parts of the unreflected wave in terms of they're going to travel a different distance. These all presumably travel the same when you initially shoot it and it goes right to the other receiver. Well, I could put an arrow on the emitter. That's the emitter. Yeah, well, I'm just saying, as soon as you have a reflection, then you're changing the distance. Now, the distance, though, just depending on where you put this thing in the middle. So the more you move it, like, if you have it at the half phase position, then it will reflect and be at this new position, halfway. It could be halfway between the two. And so you're creating new phases. Now, so we're still going to argue about whether something's getting phase shifted when it goes through the antenna. So the other argument is that when you put the second filter, when you put a filter in, what it might be doing is, I probably should just redraw here. Alright, so another explanation is what happens. So this is the part that got me thinking. So you have this is just, say this is just one bar of the thing in the way, the filter. The idea is the radiation is hitting it, some portion of it, and I would argue what happens after that is, does the radiation come out the other side? Now, it seems logical that it would. I'm arguing that it certainly reflects. So you definitely have a portion that goes back to the emitter in every case. But the point is you have electrons moving now inside the metal by the theory I've provided. Okay, it's the simple idea that the electron already has bits inside. You make an exchange, you put one in, you get one back out, going the opposite way, and the electron gains momentum. That is, it itself changes its bias, and now has a bias in this direction. There's no violation of conservation of energy because I've already stored energy inside the electron, and all I've done is make an exchange that changes the ratio inside the electron from 3 to 2 to 2 to 3, and that means there's a direction change. Alright, so we are moving electrons inside a piece of metal, and that movement, unless it's stored as heat, will have to leave by conservation laws. And the argument would be is that it's going to leave in some form of radiation, and why not be the same kind of radiation that went in the sense that the electron will do exactly the opposite thing it did when it got hit by the radiation. It'll make an exchange with the universe. It will now absorb a fellow going this way, and it'll emit one going this way. And so it will retransmit what came into it eventually. And every time these retransmissions happen, like on the surfaces of substances, that's essentially what happens when light hits a surface, is there's this equal and opposite reaction. The reflection you never see because you're never the emitter of the light. It goes right back to the source. And you have an interaction in the surface, and when the light comes out, okay, it'll be out of position, so I should have drawn that better. And a little bit off, because of the refraction, and the light will come out deflected a little bit, but at a parallel. Okay, so now if it went straight, it would be there. Instead, it's going to be on a parallel path. That's a little bit off, depending on the thickness of the glass. let's say it's glass, and where's the other point I wanted to make? Well, anyway, so it is transmitted through the material and comes out in this coherent form because of the conductivity, you could argue, or the rigidness of the substance. So metals are all crystals, they're rigid, they conduct quickly. So the argument would be is that this is kind of a conduction here. And it does take time. I mean, the light takes a lot of time to be conducted. It's not moving as fast, the energy, because it's in the form of electrons. Electrons move from this surface to this surface, and they move at a different speed. And that means the phase coming out will not be the same as the phase going in. And often these phase shifts have a percentage. They're half off, or they're kind of a rigid percentage that the phase is now changed based on the travel through the material. All right. Now specifically they can measure that, I'm not quite sure, so I don't want to. I don't want to say it's automatic, because it might not be. It might be material specific, and it might be to some degree that we can't detect. Detecting half phases in stuff as small as light isn't all that easy to do. But anyway, all right, so that's probably enough of that. So the other point, so what I was thinking, the extra new bit that's kind of interesting, is if you thought about glass or water or anything that deflects light, so anything that does this surface thing. Come on, marker. The idea is that you have this angle change. Okay. I was thinking about that in terms of the antenna argument. And so here's an antenna receiving this impulse. The electron is now excited. And my argument was I was just thinking about, well, what is the consequence of that? Well, in a conductor, that means that this atom that this electron is attached to is now positive pressured. And we know that the pressure moves to the other atom. So if there's another atom next to it that's low pressure, smaller, it's going to share that pressure, and the two of them are going to equalize, and the pressure will, in a sense, migrate through the conductor. Now, the key to thinking about this is why does it always happen that it seems to move through conductors the long way, and it always ends up moving. It's the obvious argument is if things were going to polarize, they would obviously polarize more, plus minus to the longer distance, because then the electrons are further away from each other than polarize this way. Now, it would polarize all the ways, but the point is that you have a lot more polarization in one direction the longer, because they're obviously now the electrons can get really far away from each other. So it sort of goes with my point that electrons are always repulsive. Even when I have them 10 miles away from each other, they still don't like each other. So they're always tending to get as far away. The tendency through all their interactions is going to be the electron will be the most stable, the happiest, the most comfortable when it's as far away from all the other electrons as possible. That will be its most comfortable position. So if you're getting into a bunch of chairs, the chair you like is the one that's most comfortable. That's the one you'll stay in the longest by odds. And so over time, the electrons will all tend to find more comfort the further away they are from all the other electrons. Even though there's more protons over there, that balance has to be maintained, of course. The attraction to the protons and the repulsion of the electrons. So, in a sense, they're going to try to do that. They're not going to succeed, but that's going to be their effort. Okay, what else is there to say? So taking this out of here just for the sake of the drawing. So what I was thinking is that the current's going to move in a direction because there's going to be lower pressure. So let's just assume that there's a little bit lower pressure at one end than there is at the other end. So the atoms are going to exchange pressure in that direction. And as they're exchanging it, there's still this momentum in this direction. Okay, so the direction they got hit still has momentum. The electron got hit in this direction. But the consequence of that was to polarize the atom. That is, especially you can see in paramagnetic metals, that's essentially what happens, is you create more than one phenomenon. So as you put the pressure in, you polarize the atom. That is, you make it magnetic. You turn it into a little mini magnet, plus, minus, north, south, however you want to look at it. And at the same time, you create a current, electricity. And so sort of what I'm arguing is the tendency is for the electricity to move through the antenna. And we know that the antenna is grounded. And so the ground is going to be the place that it's going to head, the current. Well, obviously, the Benjamin Franklin thing screws this conversation up a little bit. But let's see if there's a way to explain that. Well, let's just say for the sake of the argument, ground is negative, and it's probably the other way around for the sake of the argument. But anyway, and so it's going to tend to move in one direction, so that's sort of the right-hand rule. And so as it's moving, so the pressure came in this way, it's going to create a current. The atoms are going to exchange pressure in this direction, all right, and what you end up with is some sort of path and then a readmission. Now in conductors, good conductors, this direction happens really fast, so there's probably a lot of deflection, a lot of displacement. And in insulators or bad conductors, it happens really slowly. It doesn't conduct the differential very well, and that's why you have only a little bit of this refraction, where the light gets bent. So it's in a conductor, this line would be, radical, where in a non-conductor it's slower process, so it doesn't, it comes out less deflected, less moved by the fact that at the same time the energy is moving this way, it's also moving through the atoms this way, and so it ends up coming out this way. That's sort of the argument. And I think it sort of fits. So I'm just saying it's interesting where one thing leads to another thing, leads to another thing. So I think I sort of explained this connection. So this, the movement is more about the conductivity of the glass. Now, why it bends this way rather than this way, I don't have a great answer for, at this moment. Beyond saying that it obviously has something to do with the momentum of the electron, and somehow it's anti that momentum, down from that momentum, wherever down would be in terms of viewing it. It can't go this way. Well, it can as a reflection. So I guess those are the two choices. It either reflects or it has to go the other way, because it can't add energy, so it can't go in a positive direction. It has to go in it has to sacrifice to move the electron, so it can't go in a positive direction. Well, anyway, I have to think through that one. But anyway, there's this crude similarity in terms of the two things do seem to have some connection. So I think that may be worth pursuing in the future. All right, so we're still stuck with the argument about, from what we've seen in the experiment. Like I said, is the idea of detecting these phases, and somehow why does the filter So what we have is, in the radar experiment, we have a filter, okay, where this distance is much smaller than the wavelength, like 10 times smaller, something like that. Okay, so it's it's intuitively doesn't make much sense why a wave of this size, all right, finds comfort in getting through a filter that size. So that's part. You can't just say, oh, it hits this part or it hits this part, because obviously it's hitting a lot of parts. So the filter's the wrong width to say you're hitting the on parts or something. There's a bar where this on is, and that's the key to it. It's got to be more complicated than that, because the filter's narrower than this wavelength. So that doesn't really work as an argument. So what I would argue, just off the face of it, is okay. So you have the admitting polarization is in some direction, and the receiving has to be in a certain direction. And what's happening is when you put the filter in, what it's doing is it's there's an antenna producing. You're putting essentially another antenna in the field, in the sense that it reflects the energy, but it also transmits the energy. And it's displaced when it transmits it. That is, it's out of phase, but it's transmitting it. And so that's what you're receiving, is the new orientation. And so the orientation is now close enough to be received. So I guess the way to do another test for the experiment is to take your two horns, all right, and face to face, and just see how much out of alignment you can turn one of them. If you can have it at 45 degrees and receive any signal, that'll tell you something. I mean, how horizontal does it have to be before you get no signal? And so that would tell you, that would explain it. So if it is 45 degrees that you can still get a signal, even though you have the horn 45 degrees out of alignment without any filters, then that'll tell you that what the filter is doing is, yes, the transmitting filter can see this filter. It essentially vibrates all of these bars, and now they're producing as if they were a emitter at this angle, and this angle can still be received by this. So you're just saying that at 45 degrees out of alignment, so I have two antennas. So I have an antenna, radio antenna, and I put the other antenna 45 degrees to that antenna. So now I'm not as bad as horizontal. Horizontal, I know I'm dead. I'm not going to get hardly any energy. But at 45 degrees, I can still get some percentage of the energy. And if I am retransmitting it, then I can essentially take energy that might not have made it, and I'm resending it at the new orientation. So you could send it at this orientation, and this antenna is now going to send it at more like this orientation. I don't know how to draw that exactly. It's going to change the plane that the signal will be sent at. So it's sending this way, and it's going to hit an antenna that's this way. It's still going to be able to collect some portion of the energy, and it's going to readmit it now this way, which is a lot closer to this way. So you've made a slight correction in the part that actually hit the antenna. Or I have to think through that one. Yeah, that's the argument. The 45 degree angle is just enough, so now the receiver this one can receive it, okay, and it's readmitting it at that new angle, which can be received by this one. So that also works as an explanation. And it really doesn't have anything to do with polarization. It just has to do with the strength of the signal and how much signal you can receive. So that would probably be enough. And again, that has something to do with the light polarization in the argument that I'm making about light polarization, in the sense that the filter in light polarization is not consuming the energy. So it doesn't get hot. It doesn't keep the energy that comes in. It is readmitting it. So even the photons that are hitting the bar and the ones that miss the bar, the only difference between those photons essentially is that their phase has been changed. And if you change the phase of the individual photon, that essentially means you took out one of these humps and you replaced it over here. Somehow the energy is over here now. That breaks the frequency. And until you put that energy back here, you don't have any frequency. You don't have a detectable photon of sufficient size, ray length. So again, if somebody has some defense or some explanation for what is conventional physics' understanding of a photon, is a photon this? Okay, if I just sent this through space, okay, 2 nodes here, node here, okay, and a node here. If I send just this through space, can I detect it? That's all I'd sent, just that. Or do I have to send this and then more of this? What's the answer? Is this a photon that's detectable? I think they know when they think about it that no, it has to be a few of these, okay, to be classified a photon. And the fact is that that photon can be 20 of those, or it can be 10 of those. And all that really matters is it has to be at least 6 for the electron to be sufficiently moved, okay, momentum in the electron, to create what we can say a detection. So there's only a detection if we move the electron enough. You need 6 of them for our eyes to move it enough. And if I provide 8, the extra 2 aren't going to make any difference. They're not going to make the electron move faster or slower or change anything. The only thing that matters is the frequency. That is, how fast do I hit the electron, because it's the speed that will ensure that the electron doesn't move this way and then move back before I hit it again. It has to kick it out of the tension the electron is held in to its proton. And to kick it out of the tension with the proton, it has to hit it at a certain speed that's faster than the proton can react. The energy from the proton has a certain amount to it, and you have to come in with more in the same amount of time, okay, to kick it out. So if you don't provide the more energy quick enough, you won't kick this electron out. But that's the only way you can rationally make their theory work. And then you have to start explaining, once I tell you your wave has to have a length to it, I mean, aren't we really just creating rays then? And don't you have to consider, don't you have to just concede it's a ray of light? It's not a wave of light. And that the wave really only has one characteristic that matters, and that is the on part, the off part, the on part, the off part. And then doesn't it just make sense to just think of it as a clump of momentum? Clump of momentum, clump of momentum, clump of momentum at a frequency. That's physics. That's quantum mechanics. Alright, that's probably enough. So anyway, there's, I got some food for thought. I have to think through it some more. And maybe Steve can do a few other experiments playing with this, moving the filter through the space and figuring out what the distance is, 3 centimeters, well, that'll sort of say, okay, it is picking up the phase somehow. Okay, phase is important. And phase would be important based on reflective distances. When you, just like a trombone, you change the distances, you're really just changing, well, you're changing the frequency, but changing the size of any resonator, you change the phase of the stuff coming out. You may also change its frequency, but I'm just saying you change its phase. And changes in, well, I don't want to get into the conversions. So, yes, there's all this subtlety to it. I'm sorry, this bottom part probably didn't show up, but you probably got it from me saying it well enough. Alright, so, we'll call that a video. Hopefully the audio is okay. Anyway, sometimes if I talk behind here, you can't hear me. I do have to be careful. So anyway, until the next time, I'll give it, like I said, it's an interesting subject. It's all these little subtle differences. I mean, there's a difference between the antenna and what information is carried on the photon. So again, do you really think that when a photon travels from a radio antenna, that the photon has in it data relevant to the fact that the antenna was 500 feet tall or 200 feet tall or 100 feet tall? Do you think the individual photons have some kind of information inside of them that says how long the antenna was? Now, do you think that? Just curious. I don't think that's very reasonable. But anyway, I mean, it's reasonable in the sense of everybody says so. Based on the theory you've been taught, but I just mean it just doesn't make any, it's a little hard to draw the picture of that, I think. Alright, anyway, drawing pictures is good. Wish more people did it. Like I said, they just don't draw photons, they just give a squiggly line of undefined length and say that's a photon. And it's sort of important recognizing this length problem. And as I'm pointing out, if you're going to mess with the individual photon, what are you going to mess with? You're going to mess with the placement of the quanta inside of it. Anyway, till the next time and such. But, I mean, Steve ought to just come clean. He just let me know what his theory is so I know what he's looking for. And, but whatever. I guess it doesn't it's not essential. The experiment speaks for itself, but again, see, that's part of the problem is that the experiment is too crude. It's one thing to say, okay, let's see if the vague idea works. But the vague idea, doing it simple, like we don't worry about how aligned anything is, we're not being very precise, it's just a little bit dangerous when you draw conclusions on an experiment that wasn't done very carefully. I'm just saying. It's a little dangerous. Yeah, it doesn't mean it's guaranteed disaster. It just means you got to be more careful. You got to be a little bit careful about your conclusions. That's all. Okay. Till next time. And such.